Welcome, everybody. Good morning, good afternoon, good night, good evening for people in different time zones. This is Gokul IYER, and this is the session on methods from where we left off yesterday. So we have a packed session today with 6 speakers. So with that, let me request Jan Bakes from the Integrated Assessment Society to go ahead and share his screen and start his presentation.
Hello, good day everyone. My name is Jan Bakkes of the Integrated Assessment Society and also a little bit of PBL in the Netherlands. I want to speak about the combination of 2 ideas.
Yeah, Jan, a quick question. Are you sharing your screen?
Yes, I've done so.
It doesn't show up for us.
Okay, let me. Is it should allow something?
So if you're using a Mac, then it could be problematic. In which case, it might be easy for me to drive it.
Yeah, Firefox is playing up. Okay, I'll do the PDF then.
Okay.
I have to go there.
So I have your presentation on my screen in case you want me to drive it.
No, I have to select the file. I'll go down that whole tree. Sorry.
No problem.
AnyMeets is working on the file. Is it visible now?
Yes.
Okay. I'm not sure how to flip through the pages, but we'll see. Okay, I want to speak about the combination of 2 ideas. One is renewing the principles of integrated assessment, and the second idea is that this may well present an opportunity for joint work by IAMC and TIAS, the Integrated Assessment Society. And I want to put this on the table as a suggestion, and therefore I end with questions to the audience, and we will see how that has to be handled because there's limited time for discussion. Yes, so this is the most important slide. Thank you. It's about integrated assessment in the next decade, the 2020s, and also about IAMC and TIAS. Now, integrated assessment, the common understanding is that this is a meta-discipline that integrates knowledge about a problem domain and makes it available for societal learning and for decision-making processes. And typically that's future-oriented. And I won't say this every time, but I'm speaking of integrated assessment in relation to environment and development, and sustainable development. This circuit that I'm part of understands assessment as both a process and the product, the report that comes out of it. And all the skills that you need for those 2 components, process and product, design, involvement of players, the delivery, like delivery John Sturman spoke about yesterday, that whole craft for me is part of integrated assessment. Now, apparently that toolbox has been very useful. If you look at the past 20 or even 30 years, there's widespread application. Much has been learned. There's a growing community globally, like IPCC climate assessment reports, but also the Global Environment Outlook, IPBES, but also more locally on MaREI Nexus projects. Backcasting has made a new appearance. Also even in social impact assessment methodologies. And there's also a host of new practitioners in various regions of the world. Against that background, about now would be a logical moment to look at what we have learned and look at new challenges on the horizon. And there's a few, like the changing information needs as we move from agenda setting to options for action. Also new challenges in an important user category wanting stuff on their phone now, so immediacy, which is very different from, say, the mid-90s. There's also a widening scope, more attention for social implications, for feasibility, for regional context, for very complex situations like urban environment. And also the SDGs by themselves are a good representation of the widening scope that needs to be addressed in integrated assessment. In addition, many practitioners find themselves in a multipolar and an increasingly crowded landscape. Multipolar in the sense of a diversity of interests, diversity of time horizons, therefore, contested science even, and the crowded landscape. Well, look at the number of integrated assessments and models that are around. So that's something to be reckoned with in the 2020s. And in addition, integrated assessment often is a somewhat loosely used term. Some people would call integrated assessment a study that looks at the whole of a causality chain, includes recursive modeling, or covers a wide range of subjects like in Nexus work. And I was struck also by the fact that some studies that should be called integrated assessment are not using that term. It's also the other way around, that some simple studies are calling themselves integrated assessment. So a bit more of a definition there might be useful. So there's one side, one idea. The other thing is that in discussing with IAMC colleagues, Detlef van Vuren, for example, also John Wyand, we were struck by the fact that those two organizations, IAMC and the Integrated Assessment Society, are almost of the same age, at least in terms of their present organizational forms. Both are from the early 2000s. They cover a similar circuit, at least in terms of the knowledge organizations that are involved. And they also deal with related topics, not exactly the same, but related. So perhaps there's something of a synergy potential in doing things together. Now, I'll come to a concrete idea about that, but first a sidestep about the Integrated Assessment Society, because not everyone may be familiar with us. I'll try to do this quickly. This paragraph is how we define ourselves: a community of interdisciplinary and disciplinary scientists. As I said, IAMC and the Integrated Assessment Society are almost at the same age, although TIAS had a bit of history before that. And unlike IAMC, the TIAS membership is hybrid. We have individual members, but also 8 institutional members, but also reach out to people who stayed on a circulation list, and we also have a readership of a newsletter of people that are not members. So it's a bit more diffuse than IAMC to attach a number to that, but I would say normally we reach at least 150 and occasions 250 individuals. But I'm not sure about that because of the way we are organized. The sort of things we do. Nowadays, a newsletter, no longer a journal. Webinars are the most important form of our activities. We became almost an exclusively online community even before COVID. Typically, we run 3 to 4 webinars a year. An interesting share of those are organized by an active learning community. That's a group of TIAS members that looks at capacities to learn from assessments and how to design assessments so that learning is better facilitated. Things like narratives, games, connection to education, also how to measure the learning that takes place. And we also, at least until the mid 2010 years, organized summer schools or winter schools, depending on your hemisphere, on integrated assessment. It used to be very lively events. As a matter of principle, we seek collaboration with complementary groups like IAMC and the policy community, like the European Commission, for example, like OECD, like UNEP, etc. And this is why I'm holding this talk, because of exploring collaboration. Finally, but I won't go through the details there, there's a number of names and also countries associated with those names of people who are taking up a role, have taken up a role in TIAS. You see our good presence in Western Europe. That's an inheritance from how we started, namely as a EU-funded project for 8 years, but also people in Australia, China, Kenya. Not shown here is that there's an active chapter of TIAS in Latin America, run collectively from Mexico and Argentina. Now, back to the subject of integrated assessment principles. If the idea is right, this is a good time to look at those principles again after a couple of decades of practice, then there's a choice of what you want to get out of that. Do you want criteria as they exist in the evaluation community? Imagine 2 pages of text describing what integrated assessment is. Or do you want something even more fixed, like an ISO standard? Or do you want something at a higher level of abstraction, covering a greater diversity of practice, and that will be principles? Now, when we thought and discussed about this in TIAS, in a webinar and a working group, our idea was that principles is perhaps the most suitable form for a thing that you want to get out of this, because there's such a great diversity of practice in integrated assessment. And then we realized that something like that exists. That's the BAKKES principles for integrated assessment in relation to sustainable development. And even more strikingly, there is 2 editions from that now. The BAKKES principles, as they're known, were established in '96 and then revised in 2007. In that case, by the exercise was led by IISD and the OECD. The OECD coming from the measurement side of things. So apparently there seems to be a habit forming of revising these principles every 10 years. So, but now would be a 3rd revision. That seems to fit. And importantly, if you take that form of reviewing principles, as was done in BAKKES, as guidance, it also points to a 3-fold audience, namely the makers of future assessments, like the people in this conference, but also people commissioning future assessments. It points to in-between parties, knowledge brokers and media. For example, those 2 BAKKES conferences had presence by Financial Times and experienced journalist of CNN, and that was very useful. And then it would also aim at users on both sides of the science policy interface. So the likes of Tom van Ierland, the European Commission, but also people at universities and science boards who program the development around new data, new tools, new approaches, and any gaps that might come to the surface in reviewing practice on integrated assessment. And just to give you a glimpse of what the BAKKES principles are, I'm not going to talk you through it, but you see here keywords that you probably recognize from your own practice. There is references at the end of my presentation if you want to look up more detail. This shows the 1996 version, the 2007 version compressed this a little bit, came up with more crisp language. So revision is also good for making this more condensed and easier to convey to people. And then almost at the end, if this sort of thing is going to be undertaken, there's also a choice of format for the review. Process is at least as important as the thing you get out of it. If you assume that a format as the previous BAKKES reviews would be followed, then that would be in the shape of a workshop with the number of people that fits around the table, and that's about 20. That's not many. So it has to be by invitation and well prepared. One of the preparations should be an input paper, like was done in 96 and 2007, that lists the challenges, the various practices to be considered, and perhaps also a reflection on the next decade, what is on the horizon. And you probably want to prepare that with input preparation sessions like side events at a conference. People from the media would probably call their colleagues. And that is important because the eventual workshop by invitation will be so concentrated. And then probably because a review would be based on cases, on practice, in addition to looking into the future, you probably also want papers on the individual cases or circuits of practice that describe how the principles relate to that body of experience. That worked well the two previous occasions. And you probably, because this is forward-looking, want to review not only the existing principles, but also focus on one or two challenges on the horizon. Perhaps the whole cluster of transparency, robustness, etc. of complex assessments. Perhaps also the balance between the 10 or so principles, and perhaps something very specific for the climate-related community, the increasing challenge of vast quantities of literature that have to be taken into account. This focus is a bit more open than the previous things I mentioned. There's more ideas about this mentioned in the short paper that I uploaded, and even more in the challenges paper that has been prepared and is downloadable from the TIAS website.
Jan, just a quick time check here. We're running a little over time, so if you want to present your last slide with questions, that might be useful.
Okay. Okay. Here's a slide with the current status. I'll skip that then, but the main point is that I'm wondering whether a next push should be done together with IAMC. And then, indeed, here's the last question. That's a question from me to the audience. Whether or not this rhymes with your agenda perhaps as IAMC, or your knowledge organization, or as individual in your practice. What do you think of what would be best if you think it rhymes to join as individuals, organizations, or make it indeed a TIAS IAMC joint thing, and any other suggestions? That's it from me. I'm looking forward to your responses and also to a moment to discuss those.
Thanks, Jan, for the engaging presentation and for getting us started this morning. To the audience, I would recommend that you respond to Jan's questions directly on the chat, so that we can move on with the next talk. We're running a little over time right now, so I think it might be most efficient for us to move on while people can post their responses via chat or reach out to Jan for direct responses and direct correspondence. Jan, may I request you to post those questions you had in the last slide onto the chat so people have them in front of them, and we can start a discussion in the chat section rather than
will do.
Yeah, and then we can also have a follow-up later on if required with key players from our community. But thanks for getting us started. With that, I think we can move on to the next presentation this morning. So James GLYNN from University College Cork to talk about TIMES-GEO. James, the stage is all yours.
Thanks, Gokul. And sorry, John, I didn't mean to push you off by sharing my slides too early. I also need to apologize. For some reason, Chrome is not allowing my camera to work, so you don't get to see me from Ireland. But good morning from Ireland. So great. I'm presenting our development work on TIMES-GEO. So it's a new global times model, as Gokul says, and also methods that we're trying to explore with colleagues to look at the impact of climate variability and extremes on how the energy system operates. So, so the Chimera project, first off, an introduction, is a partnership program between UCC in Ireland, Tsinghua University in Beijing, and Peking University in Beijing. We're in this piece of work exploring the benefit and need of high temporal and spatial resolution in energy systems models. That's one of the key goals of the Chimera project. In this presentation today, I'm just going to explore developing a method for coupling detailed Earth systems models with detailed process-based energy systems models, which unfortunately we share nearly the same acronym, and to explore the variability and extreme climate events on the energy system. So we know that renewable energy potentials will vary in the future. We know that there will therefore be operational variation from changing weather impacts. I think, Gokul, you presented early on in the week on changing heating degree days and cooling degree days. We also want to look at extreme climate events. So how do future climate extremes like flooding impact on energy infrastructure, and how does that shut them down? Or what are the damages? And then how do these interactions, how do these climate impacts change our long-term energy systems planning? So this is going to be a whistle-stop tour. This is going to be 10 minutes. So I'd really welcome any questions, criticisms, suggestions as to what we're doing and the way we're going in developing this. So TIMES-GEO is still under development in this project. It's a 4-year project. We're about halfway through now. So it's developed in the TIMES framework from the IATSAP. So the source code is now open and available at the ATSAP GitHub. So we're taking the same, or the typical TIMES process-based approach.
James, who will be talking about hourly time resolution and fine spatial resolution in the TIMES-GEO model. So James, I remember that you had presented a couple slides early on, but I think you can dive into the model directly to save time.
Okay, great. I'm obviously not going to get through all this, so if anybody has any questions, please type them up, and I'll get back to you as I can. So, as I was introducing earlier on, we've developed this new TIMES model. It's increasing spatial resolution to 31 regions from the old TIMES-TM type models from 15 regions, but more so looking at more technical resolution and spatial resolution. So for this work, we're exploring having sector specific, so having regional definitions defined at the sector specific level rather than on the aggregate global level, so we can have sector specific regional definitions for the power sector, for example. So we're hard coupling a 250 region Plexus world power systems model that was developed by colleagues in MaREI-UCC, Martin Brinkerink and Paul Dean, and trying to hard couple this into TIMES. So that global power systems model is available on Harvard Dataverse for anybody who wants to have a look at it. So within this power sector, we're introducing unit commitment and dispatching into TIMES. So colleagues of mine, Dr. Xufeng Yu, already demonstrated our test case of this earlier on in the week for Ireland. So in the global example that we're developing, we have the global power plant database from the World Resources Institute in DC and from Google. So we've got location, capacities, power plant by capacity and by fuel type. We have wind and solar hourly capacity factors for each of these dots in 2015 from climate reanalysis data, and we have hydro monthly capacity factors for each existing power plant, and then we assume unit commitment dispatch features categorized by each region and the vintage from which the power plants were installed. So we have each of these power plants, and then we have so these are the current power plants in 2015, and then we're trying to aggregate the future power plants into 258 regions rather than the 31 regions in TIMES-GEO. So as I said, we're trying to explore this temporally and spatially high resolution variable renewable energy system with capacity factors in this model. So we're incorporating existing wind, solar, and hydro plants from climate reanalysis data, and that we know that within both the power systems models and TIMES type models that renewable power plants are going to get priority dispatch. And then we want to use future climate models to scale existing capacity factors so that we have we have existing capacity factors for each different renewable energy system, renewable energy technology. So for hydro, for example, in China, we have these monthly capacity factors existing, and we want to scale these based on climate reanalysis data. So we have climate models that are projecting on half-degree gridded scales. So we have wind speed, solar radiation, hydro runoff for 3 different scenarios. So SSP1, SSP3, and SSP5 for different temperature goals. And we're trying to incorporate these scaled capacity factors at the resolution for each of these technologies into our TIMES-GEO model. So we get capacity factors that are running for kind of changed future climates, but we also want to explore extreme climate impacts. So in the RCP 8.5 type scenarios, if there's high flooding events or high storm events, how does that shut down infrastructure in certain regions, and then what are the cost impacts of those events? I'm going to get cut off any second. So just to conclude, so we know that others have shown that integrated assessment models can underestimate dispatchable reserve power capacity and overestimate variable renewable power capacities by ignoring power systems operation constraints. Given the level of electrification in our Paris Agreement compliance scenarios, we probably should aim to improve the robustness of electricity operation dynamics within our models. Within this 250 region, hourly time slice resolution creates a massive sparse solution matrix, which is inherently difficult for us to solve and requires a lot of computational memory to compile before even running. So these are numerically very difficult problems to solve and to optimize. So we're still developing how to do this. So we have the data, we have the model formulations and the source code that can run this. We've proven this at regional scale, but we're at global scale, we're pushing kind of optimization algorithms to their limit to solve these global dispatchable problems. So we need to reformulate our base year model so that it's more efficient in memory space, so that it's less sparse, so that it's easier to solve. And this will also enable us to take advantage of high performance computing facilities rather than just high process speed facilities. So there's a few optimization algorithms that are promising that will help us solve these really massive matrix sparse problems. One of them coming out of the BMME project with DLR in Germany. So I'm 2 minutes over time. I'll stop there, but please, if anybody has any questions, I'd gladly answer them, or even just have a chat about what we're doing. Thanks very much, Gokul, and thanks for the time.
Thanks, James. I'm gonna give a moment to the audience. There are questions for you in the Q&A. But in the meantime, I have one question just for discussion with you. So how do you see your approach complementing or addressing some of the issues with low duration curve based approach that most power sector models, including many of the IAMs that have power sectors represented in them, take to where we just use some sort of a sorting algorithm to sort hourly loads, or even like just combine a number of hours together into multiple segments instead of going to the hourly scale. So how do you see your work complementing or addressing some of the limitations of that approach?
Yeah, I think the main improvement is the idea of chronology. So, when we started looking about storage and the interaction between transport systems and electricity systems, the low duration curve idea is really computationally efficient, but it doesn't take into account chronology, which isn't a focus of what we're trying to do, but it will be useful in the future to try and take into account hydrogen storage, battery storage, and the idea of chronology within our model.
Right, and in terms of computation, have you tested a comparison between the two approaches, or do you have a sense for how the two approaches might compare?
We haven't compared it, so we don't use low duration curves in our model. We generally just have kind of static capacity factors by region, by technology, but I haven't used low duration curves.
Okay, got it. So with that, I think we can move on to Jennifer Morris from MIT. Who will be talking about probabilistic uncertainty quantification methods in IAMs. So Jen, do you want to share your screen?
Great. So my name is Jen Morris. I'm a research scientist at the MIT Joint Program on the Science and Policy of Global Change. And the work I'm presenting today is on a consistent framework for probabilistic uncertainty in coupled human-Earth system models. And so many coupled human-Earth system models or integrated assessment models have been developed to explore potential future energy, emissions, climate, and other outcomes of interest. And the MIT Integrated Global System Modeling Framework is one such model. However, uncertainty in these models is often represented through sensitivity analysis, scenarios, and model comparisons. And these exercises are useful and can provide great insights. However, they can also limit the uncertainty space explored, for example, by focusing on just a handful of defined socioeconomic pathways. And they also provide no probabilistic interpretation. So this study takes a probabilistic ensemble approach to representing both socioeconomic and climate uncertainty, with the goal of developing probability distributions of key outcomes that can then serve as a basis for risk-based decision-making. So our approach for representing uncertainty employs a Monte Carlo analysis. This involves developing probability distributions for key parameters in both the human and Earth system components of the coupled models, and then sampling from those distributions to construct multiple sets of parameter values that span the uncertainty space, And we use Latin hypercube sampling to limit the ensemble size. And then, using the sampled parameter values, we simulate large ensembles of model runs of our human system model linked to our Earth system model for a given policy scenario. And the result is probabilistic, internally consistent, integrated socioeconomic and climate projections that can give insight into the probability of outcomes of interest, such as emissions, concentrations, temperature, precipitation, GDP, energy, and others. Now, these estimates of future uncertainty are conditional on the model structure, on the distributions of the uncertain parameters, and the assumed scenario settings, including the policy assumptions. In terms of developing the probability distributions for key model inputs, distributions for socioeconomic parameters are based on historical data, expert elicitation, and scientific literature and modeling, and there are correlation structures imposed on related subsets of parameters. And the Earth system parameter uncertainty is estimated using an optimal fingerprint approach, which uses historical data on climate, ocean heat, concentrations of greenhouse gases and other pollutants to estimate a joint distribution for climate sensitivity, ocean heat uptake, and aerosol radiative forcing parameters. In our framework, we take policy to be a deep uncertainty and use a set of scenarios for our ensembles. These include a reference or business as usual scenario, what we call a Paris forever scenario, which assumes the Paris NDC targets are met by 2030 and the policy levels are retained thereafter. And then two stabilization policies, Paris 2C and Paris 1.5C, which both assume that the NDCs are met by 2030. And after that, there's an emissions cap with a global carbon price designed to ensure that the global mean temperature does not exceed either 2 degrees or 1.5 degrees with either a 66% probability or a 50% probability. So here are the results for global emissions for each ensemble scenario. And I've overlaid them over the RCPs to provide some context. And there's only uncertainty around the reference and Paris forever scenarios, as the 2C and 1.5C scenarios must meet the same binding global emissions cap in each ensemble member. Overall, the scenarios span the RCP space fairly well. The reference scenario has the greatest uncertainty. Compared to previous analyses, the range is more narrow, and this is driven by updates to the probability distributions and updates to the human system model, including slower economic growth, particularly for China, falling costs of low carbon energy options, particularly renewables, and government interventions worldwide directed at expanding the role of renewables and other actions. So these all lower the high end of emissions. Another point is that variability of many countries and regions tend to offset one another, making the variability at the global level much lower. Another point to make is that although the 2C and 1.5C scenarios must meet the same global emissions trajectory, there is uncertainty about how those emissions are distributed across regions and sectors, since emissions trading is allowed, so we can also investigate that uncertainty. Here I'm showing results for temperature, and at the end of the century, the median temperature change relative to pre-industrial levels is 3.5 degrees Celsius for the reference, 3.1 for Paris forever, 1.9 for the Paris 2C, and 1.5 for the Paris 1.5. Importantly, climate policy lowers the upper tail of the temperature change distributions more than the median. For example, if you compare the Paris 2C distribution on the right in blue to the reference, the median temperature is reduced by 1.6 degrees, but the 95th percentile is reduced by over 2 degrees. And so this indicates one of the greatest roles of mitigation action, which is to lower or eliminate the likelihood of extreme temperature outcomes. So this is highlighted by looking at how the percentages of runs exceeding a given temperature level varies across the ensemble scenarios. And results indicate that even a relatively modest policy, such as the Paris Forever, can significantly reduce the likelihood of high temperature outcomes, such as the 4 degrees. The Paris 2C essentially bounds temperature at 2.5 degrees, while the Paris 1.5 essentially bounds temperature at 2 degrees. Also important are the lower tails, and so under reference in Paris Forever, the 2C target is essentially out of reach. And another insight from these results is that due to uncertainties in the climate system, a given emissions constraint can't guarantee a particular climate or temperature target is met, but rather emissions targets would need to be adjusted over time as the uncertainty in the climate system is resolved. To help communicate these results, we also present them as roulette wheels, or as we call them, greenhouse gamble wheels. And we ask the question, which wheel would you rather spin? And of course, the follow-up question is, how much does it cost to spin a policy wheel? So for all ensembles, GDP is endogenously determined in the model and therefore uncertain. And it's important, it's important to note that climate impacts and feedbacks are not accounted for here. So this is the policy cost on GDP. And here we focus on results through 2050. And relative to the reference scenario, global GDP in 2050 is about 2% lower under Paris Forever, 6% lower under the 2C, and 18% lower under Paris 1.5, which shows us the significant additional cost of achieving the 1.5 versus the 2C. However, in all scenarios, GDP is growing. Here I'm showing the average annual GDP growth rate from 2020 to 2050. Again, there's a noticeable drop-off in the growth rate under the 1.5 scenario. Oops, I forgot to advance. Sorry about that. And then we can also look at regional GDP growth rates. And we can see that for some regions, like the US and the EU, the scenarios largely overlap, meaning that policies have relatively little impact on GDP. However, for other countries, such as China and India, and even more so for regions like Africa and the Middle East, GDP under the 2C and 1.5 policies increasingly diverge from the reference in Paris Forever scenario. And this highlights important issues of equity and that developing countries are likely to bear the greatest cost of global climate mitigation unless specific actions are taken to avoid that outcome, such as policy design mechanisms or financial transfers. We can also look at implications for energy, and here I'm showing the uncertainty in global primary energy by type for 2030, 2050, and 2100 under the reference, which is the darker shades in the figure, and the 2C, which is the lighter shades. And notably, the scenarios diverge significantly for coal, gas, and oil. For under the reference, all three fossil sources increase, whereas they decrease under the 2C. In terms of making energy investments today in the face of policy uncertainty, renewables offer the safest bet with the greatest potential future regardless of the scenario. So to close with some key takeaways, we can make use of information we have to develop probability distributions for key parameters. And this type of uncertainty quantification allows us to explore the outcome space, gauge the likelihood of outcomes, identify uncertainties of greatest importance or least understanding, identify components and key components and assumptions in the model, and then in turn, this can inform decision-making, guide research efforts, and also inform scenario development. So with that, I thank you, and I look forward to any questions. Thanks.
Excellent. Thanks, Jennifer. We can take one question from the audience. So Jen, we have a question from Evelina for you. Some folks have strong reservations on attaching probabilities to model parameters that involve any social, human, and even economic dimensions, but you seem to be doing that to some extent. What's your response?
Yes, so we are doing that. And so we're trying to balance, you know, some parameters or some things, social human variables, we do have information about that we can use to form some type of probability distribution. Others, there's less confidence, and so we might, you know, want to consider deep uncertainties, as we've done with the policy, and we do with some other things like the use of negative emission technologies. But for parameters where we do have information, I think we should make use of it. When we don't, decision makers tend to assign their own probabilities, and that's going to be based on, you know, their own understanding, whether it's correct or not. And so providing some insight based on, you know, information that we have from years of, you know, scientific inquiry, I think makes sense. And with the understanding that these are not going to be exact probabilities, but they give a better sense than everything potentially has an equal chance, or, hey, you just figure out what you think is the most likely. So we're trying to provide scientific insight into what is more likely.
Right, right. Thanks, Jennifer. So just a quick pointer for you. There are lots of questions in the Q&A, so that's great. Thanks for the active engagement from the audience. So please feel free to answer questions directly into the chat box there. Great.